Okay, in this video I'm going to talk about the speed of a wave and how changes in the speed of a wave require changes in wavelength. The speed of a wave is set by the medium that the wave is traveling in. This is a little bit strange. When we think about the speed of a wave, especially when we use the universal wave equation, we think that it's the wavelength, the step size, times the frequency, the number of steps we take per second. And that's our universal wave equation. But when we actually generate a wave in a medium, typically we're generating a wave at a specific frequency, and the wavelength gets adjusted to fit the speed of the medium. The speed of light, for example, in air, is given to us by a property of the material that we call the refractive index. Refractive index gets the letter N. So we say that the speed of light in air, speed, is equal to the speed of light in a vacuum divided by the refractive index. And speed of light in a vacuum is 3.0 times 10 to the 8 meters per second. With sound waves, the speed can be very different depending on the type of material that it's in. I just threw this little chart in here and we can see that the speed of sound in water, for example, is like 1,500 meters per second. And in something like granite or glass, it goes up all the way to 5,000 or 6,000. In air, the speed of sound is given by the equation V equals 332 meters per second plus 0.6 times the temperature in Celsius. So obviously this is completely different from these. It's about 5 times smaller. So the speed of sound is very dependent on the medium. For light, the speed of sound typically only changes a little bit. Refractive indices tend to be sort of in the range of 1 to say 2.4. So you get a little bit of change here. But with sound, you get drastic changes depending on the type of medium that you're in. Finally, with water waves, the depth of the water is what determines how fast the wave will travel. The idea here is that if there's a wave traveling across the top of a water, the interaction between it and the bottom of the lake is what actually slows down that wave. So if it's shallower, there's more interaction and this wave goes slower. And if it's deeper, there's less interaction between the top of the water, and so this wave goes faster. So again, this is a little bit counterintuitive. For me, the way I always thought about this before I learned this was that wave speed is set by their frequency and their wavelength. But what really happens when we generate a wave, usually it's through a vibration. A vibration has a specific frequency, and then once that frequency is set, then the wavelength of the wave is then set to make the speed of the wave match what the medium is able to carry a wave at. So the medium is really the thing that sets the speed of a wave. If we imagine waves moving from one region to another region, and they need to change their speed, the way that they're able to do that is by adjusting their wavelength. So again, if we imagine deep water, we have this wave with this long wavelength, and that moves into shallow water. Then what we see here is, let's say this wave was going at 4 meters per second out here, and when it comes in here, it has to drop to 2 meters per second. What that means then is the frequency is going to remain constant throughout this change. So what's going to have to happen is the wavelength is going to have to shorten up. Remember, again, speed is equal to frequency times wavelength. So if this is constant, and this number goes down, then this number has to go down as well. If we imagine this wave coming in at this, to this barrier, the timing that the wave hits the barrier at, T1, T2, T3, where this wave generates this wave, is constant. So that's what sets the frequency of the wave. If we imagine, let's just pretend these waves were coming in every second. So 1 second, 2 seconds, 3 seconds. The frequency here was 1 hertz. Well, the frequency that's going to be generated over here still has to be 1 hertz because that rate at which those waves hit that barrier isn't changing. So again, if we're going to have a change in speed, we're going to have to make up that change in speed in the actual wavelength of the wave. For light, since the speed is equal to the speed the speed of the light is equal to the speed of light in a vacuum divided by the refractive index, then the wavelength making up that change is also equal to the wavelength in a vacuum divided by the refractive index. So if this has to go through this change, then that change all has to be made up in a change of wavelength. For water waves, since we do not have an absolute maximum speed, they don't happen in a vacuum, we can only do proportionalities here. So we can recognize here that the speed is proportional to 1 over the refractive index. So speed 1 over speed 2 is equal to refractive index 2 over refractive index 1 in our inverse relationship. The same can be said for wavelengths. If that speed change is being made up by a wavelength, then the wavelength 1 is proportional to refractive index 1 in that inverse way, and wavelength 2 is inversely proportional to refractive index 2. We can't set a definite refractive index because we have no absolute in a vacuum type situation for water. It's always relative. Deep is relative to shallow, but there's no sort of infinitely deep that we can consider with water. So, once again, the speed of a wave is set by its medium. The frequency is set by the thing that's generating the wave, or the source. And so the thing that can make those two things work together is the wavelength, and that's what gets adjusted when waves move on different medium, from one type of medium to another type of medium, or when waves are generated in different types of mediums.